look at that. So, all right, everybody. If you don't know me, my name is Chris Kubiak. I'm the Director of Education at the Audubon Society of Western Pennsylvania. I do a whole host of various programs, everything from birds to climate change to natural history and everywhere in between, native plants, you name it. So, one of the things before I came to Audubon, I've been with ASWP now for 13 years, but my academic background is actually in history. So I have an expertise, I guess you could call that, in the early colonization of Eastern North America, but really focused on what we call the French and Indian War leading up to the American Revolution. So, why is that relevant to what we're talking about tonight? Well, when I taught at the college level history and geography, climate change and how climate and weather impact historical events and societies was a very big part of what I taught and researched. And I'd say probably the last 10 years, I've spent a lot of time focusing on two sort of past climate events that get some attention in our world today. One called the medieval warm period, and the other one that is known as the Little Ice Age, starting roughly about 1100 years ago with the medieval warm period. The Little Ice Age is a little bit more controversial when it began, but we'll say roughly about 600 to 800 years ago. Both of those names are bad because they don't really describe, I think, in total what was going on planet Earth. They describe what was going on in Europe and parts of the North Atlantic in Eastern North America, but they don't really describe what was going on across planet Earth at that time. So we're going to talk a lot about that as well. This program is also going to kind of go through the differences between what is weather and climate, because that is very, very often misstood, both by detractors as well as supporters of how humans are rapidly changing our climate on planet Earth. So we're going to talk about some of that. The physics of climate change, both past and present, are very well understood. And in fact, the physics are pretty easy. It's pretty cut and dry. And it has been known for a long time things that alter Earth's climate, both globally as well as regionally as well. So we're going to talk about that. We'll go very briefly into some of the past climate change that have gone back millions of years. But we're going to really focus really a lot of this program tonight on the what we call the medieval warm period and the Little Ice Age. So, all right. With that said, we'll have some time at the very end to also discuss if there's a few questions that you might have. So just wait till the end, and then you can send me those questions, and we can discuss that as well. All right. So, okay, we are going to pull up my PowerPoint here. All right. I always love when they do some updates here. I'm going to put on the slideshow. Let's see here. Can someone unmute themselves? Can you see my screen? If you can see my PowerPoint, please say yes.
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 Perfect. Yeah, they've altered this. They did an update within the last couple weeks, so I can't see you right now. So I'm glad you can see this. All right, let's get started here. So again, this is a three-part series I'm going to be doing. Again, this one we're going to be talking about past climate change and some of the specifics that go along with that. And then we're also going to, in future ones, talk about where we stand presently in climate change, as well as some future predictions as well here. So, and what you see in my opening slide here, this is a sort of view of Earth's climate going back, say, 70 million years ago, right? And obviously, that's a long, long period of time to kind of wrap your head around. But we do know in Earth's past, and we have very strong evidence of this, that Earth has been much, much, much warmer than it is now, and also substantially colder than Earth is right now as well. So we're going to talk about some of those reasons why here, right? This is extremely important. And I think even people that I hear that say, yes, I believe that humans are impacting Earth's climate often get this wrong, right? So we will have a warm Christmas or warm month of January or warm winter one year. And people will say, aha, it's climate change, right? Well, not necessarily. And we're going to talk about why. Now, if we see trends over periods of time, right? And our sort of stopping point now, that's the shortest interval that we can actually draw some conclusions, is 30 years. If we see trends over time of continuous warm winters, right, and warm Christmases, then yes, we can say that's climate change. Conversely, people will say, well, yes, climate can't be changing because it's been warmer in the past or colder in the past and all that kind of stuff. Well, yes, that's certainly true. And we're going to talk about those reasons why. But we really have to define some of our very important terms here, and that is weather versus climate, right? And really, it's pretty simple. You don't have to go to a college level meteorology course to understand this. But the difference between weather and climate is a measure simply of time, right? So weather is the conditions of the atmosphere or what we're having over a very short period of time. So that could be from, you know, the minutes today here on August 14th. It could be several months. It could even be 10 years, right? Averaged together. That's still technically weather because there's a lot in weather that is very chaotic, right? Climate, believe it or not, is much easier to kind of get a feel about because it is simply an average of either high temperatures, low temperatures, ambient moisture in the atmosphere, all that kind of stuff over roughly a 30-year period, right? So it's really a function of time. And in all of our past climate systems, there has always been chaotic fluctuations on a very short period of time, right? So when we talk about the medieval warm period, that does not mean that they had times and winters that were very cold and very challenging. And conversely, in the Little Ice Age, as it is poorly known, that doesn't mean that there weren't summers and winters that were warm, right? And we'll talk about some of them here. So really, weather is just short period events in our atmosphere. Climate is averaged over at the very least 30 years. So think of it like this, right? Climate is like what you expect here in July and August. You expect in Western Pennsylvania to be, generally speaking, much, much warmer than it's going to be in January and February, right? Where weather is like kind of like we had yesterday and today, right? Yesterday we had a few thunderstorms and rain passing by, and today we have sun. So that's the difference between the two. So it is very important when we're talking about past climate change. Yes, we don't know what the temperature was like on August 14, 65 BCE, right? Million years ago BCE. We don't know. But we can generalize by a lot of what we call our proxy data. So things that, while they're not thermometers, they're the results of certain climate situations that we can measure, get a very good feel on what it was like. So again, just to reiterate, weather is basically conditions in the atmosphere over a short period of time. It can change within minutes or hours or sometimes days, weeks, months, right? Climate is how the atmosphere behaves over a long period of time and space. 30 years is the shortest period you can measure, but some climate periods measure over millions of years, right? And that becomes the average regional weather pattern over decades. Okay. All right. So that's just a basic introduction. And like I said, it's just something to keep in mind is when we're talking about these past climate events, we're talking about evidence over long periods of time. So let's get with some of the basic physics here. Okay. So, some of the basic physics behind planet Earth that make climate possible, and then the various changes over time, is resulting in some of these next few things that we're going to talk about here. Arguably, thermal insulation, right? Which we know is the greenhouse effect. That's a good thing because without our atmosphere keeping planet Earth relatively warm within our habitable zone, we would be like Mars today. There is very strong evidence every year we're getting more and more that Mars used to be more Earth like than Earth is today, right? And there's some people that speculate that maybe life in our solar system began first on Mars before it began on Earth. But Mars lost its thermal insulation. So now it became a very cold and a very dry place compared to planet Earth, right? So let's talk about some of these factors that can influence climate over time. One of the biggest ones, right, which we'll talk a little bit about, is solar activity and the particular oscillations in Earth's orbit. So everybody thinks, that Earth is in a round circle constantly around the sun, and that is actually not the case. Earth will go through a number of different cycles where its orbit becomes more eccentric, and it can actually be measured pretty precisely. And we'll show this here shortly here, which it goes through these cycles that it actually can substantially decrease the amount of solar radiation hitting planet Earth, and that would greatly decrease the amount of warmth into our planet, right? Very important. Greenhouse gases keep life going, but they also, in too much concentration, can change, or much less concentration can change what the climate is over a period of time. Then we've got things like what we call feedback loops. Ice cover, more or less, can greatly impact climate, vegetation on land, or the lack thereof. Even the configuration and layout of continents is extremely important, because then that dictates where the oceans are and where the ocean currents are and how that climate evolves from there. Then things like dust and greenhouse gases thrown up by volcanoes or wind. And we know volcanoes have a huge, huge impact, an outsized impact on climate change, right? Which we're going to talk about this as well. And believe it or not, the weathering of rocks over millions and millions of years removes, particularly when rain, which has a slightly acidic uh, sort of quality to it, when it hits certain rocks with silica and limestone, it can pull carbon dioxide out of the atmosphere, right? But I don't want you to think that this is something simple and easy, right? These sort of connections take a lot of digging into to figure out, and we can, but this is not as simple as saying, "Hey, there's a volcano erupting at this time. That means it caused this." There's a lot of other factors that go into it as well, right? So these are complex interactions, and many of these factors can amplify or dampen changes in temperature in long or short term climate, right? And obviously, the greenhouse effect. I know you've all heard this. You probably learned this in general science in your freshman year of high school, or I don't know, with some of you older folks. I'm almost 50. We learned it ninth grade, but I don't know when it was taught. But planet Earth has a atmosphere that acts like a greenhouse, right? And that is a good thing, right? So when our sun comes in through that atmosphere, it will actually warm up some of the different layers differently, believe it or not. And then when it hits land or the ocean, you'll either get radiated or reflected sunlight as heat, right? And most of it will actually escape into space based on natural greenhouse effect. Some of it gets pulled back into planet Earth to warm things up. But as you can see there on the right, as humans, right, add more of this greenhouse gas to the atmosphere over time, or which we'll be talking, excuse me, we'll be talking about tonight, that you know, there are natural reasons why CO2 and methane and nitrous oxides increase in our atmosphere in the past before humans did it. Our atmosphere is very sensitive to that. And the more there is, the more that heat, instead of radiating out into space, is actually trapped in the troposphere where all of our weather occurs, and greatly then will impact the climate on planet Earth. A lot of people, again, geography is not everybody's favorite subject. Like I said, for some reason, I always gravitated towards it. It was I don't know if some people are naturals at math, other people are natural at spelling and English. I was a natural at geography, and don't tell me why. I have no clue why that was. But it's interesting, when I taught this, a lot of people, when they're looking at past climate change, and they say things like, well, yeah, in the dinosaur era or right after, it was substantially warmer than it is today. And, everything was just fine. Well, there were no humans at that time, right? So the ecosystems were very different. But it's not the only one, and it's not even probably the main one, but one of the main factors was how the continents were laid out, because what that did is that greatly impacts where the ocean currents send warmth or cool the oceans, and then by a result, cool the atmosphere as well. So continents themselves can create continental climates, right? With extreme hot and cold temperatures. If you're in a place like middle of Asia or middle of North America, or if you're closer to the ocean, like the Mediterranean or California, you have a climate that is dictated by the temperatures of those oceans, right? Or mountain ranges have a huge impact. On the windward side of mountains, right, you get a lot of rain that is wrung out, like in places like Washington and Oregon and California, where you get massive redwood trees and sequoias and you get all those rainforests. But on the leeward side, on the backside of those mountains, you get deserts, right? All of those things are greatly, greatly important in shaping climate over time, right? So, this combination of continental positioning and mountain ranges in oceans and ocean currents dictate regional climates and then overall influence temperatures and precipitation, and even affecting large scale atmospheric and ocean circulation, right? We do know when the Andes and the Himalayas and the Rockies were first pushed up, they began to rapidly, and by rapidly, we're talking about thousands, if not millions of years, but change the climate based on how they diverted some of these different atmospheric uh, winds and precipitation and stuff like that. So here's another one. This is one that a lot of people may have heard what this is. And I got, especially when I taught at the college level, I would get climate skeptics saying, well, the reason why it's warming now is because these Milankovitch cycles that, Earth is in a position where we're getting more solar radiation from the sun, which is not true. We're actually not getting more than we have any time in the last, say, several thousand years. But what a Milankovitch cycle is this perfectly timed cyclical movement related to Earth's orbit around the sun, right? And there are three of them. So the most important, I have the most important here in how they impact Earth's climate, right, is the eccentricity of that particular movement. So when it gets at the height of that eccentricity, you get planet Earth moving farther away from the sun and reducing the solar radiation that we would get from now. So during the various ice ages, when you're at that peak part of that cycle where Earth's orbit is very eccentric, we're getting substantially less solar radiation. So our temperatures globally decline as a result, right? So axial tilt. So we know that through, in summer and June 21st in the Northern Hemisphere, we're tilted closer to the, you know, towards the sun than we are in the end of December in the winter solstice. So that impacts how much solar radiation each hemisphere gets. And then lastly, what we call the precession, which we'll look at here shortly. So according to the Milankovitch theory, these three cycles combine to affect the amount of solar heat or solar radiation that's coming to Earth's surface and subsequently influencing our climate patterns. It's really simple, right? If you take a incandescent light bulb and you have the ability to turn it up and down, and you don't move it and you keep your hand in the same place, if you're reducing the amount of heat that's coming off of that, right? Same thing would be here in the eccentric and tilt away from that, you're going to get cooler temperatures. If you have more of it, you're going to get warmer temperatures, right? So it's going to impact these cycles here. So you could see here, these are on very, very well researched and understood timings where you could see the green dash is what is our, well, say right now, the cycle that we're on. But then Earth will wobble because of gravity in these more eccentric, uh, cycles around the sun between every 100,000 and 413,000 years, right? The tilt itself goes through these two different types of cycles as well, where for every 41,000 years, there are periods where the tilt is less than it is today, right? In precession, think of it like the top, spinning around, right? So it too is on a different cycle that can either bring more solar radiation or less. When all line up like they do in ice ages, where there's less sunlight hitting planet Earth because it's eccentric type of cycle, or the tilt is substantially less than what it is in our current era, and the precession is less. We get overall for thousands and thousands of years far less solar radiation as a result. So there we get into ice ages. Okay. Volcanoes and past climate change. So when we talk about the little ice age in particular, and again, that is just such a poor name for this, what really happened, but volcanoes play a really outsized role in both increasing warmth in climate over time, and also especially in the era where humans have been noticing this and keeping records, substantially reduce the temperatures as well here, right? They have both cooling and warming effects, but we know, depending on where in the continents and how big of these volcanoes are, one of those things, cooling or warming, can play a bigger outstretched role. In the early parts of Earth's history, leading into right after when the dinosaurs went extinct to about 55 million years ago, there were massive sized volcanoes across some of our continents that spewed enormous amounts of carbon dioxide into the atmosphere, and may have actually even caught a lot of some of the earliest coal beds on fire that burned for thousands and thousands of years, essentially releasing tons and tons of carbon dioxide into the atmosphere, right? More recently, while large volcanic eruptions temporarily cool the planet, they do things in that manner by releasing sulfur dioxide that in the short term forms what we call aerosols. And what those aerosols do is they act as like a mirror. They reflect sunlight. Now, they're very short lived. That usually is around 1 to 5 years in the atmosphere. CO2 that is emitted from whether it's a volcano or your car can last thousands of years in the atmosphere. So, in a short period of time, it can really reduce temperatures. But then once they dissipate, that CO2 can once again rapidly, and the methane and especially water vapor can really, really raise Earth's temperature. A lot of people talk about CO2, and rightfully so, because CO2 is a very potent greenhouse gas. But both methane and water vapor are much, much more potent in holding heat in our atmosphere. However, the difference is methane only has about 20 years as a molecule to last in our atmosphere. Water vapor will pretty much, precipitate out. CO2, those molecules last for thousands of years. So that's why we talk mostly about CO2. This is just an example of what I've sort of discussed a little bit. You can see all the various things coming out. The SO2, that is your sulfur dioxide, right? And so it will reflect a lot of light, so it'll briefly cool things. But if you get a long period of consistent volcanoes, and you get volcanoes that are underneath oceans, it can really rapidly warm our climate. We saw, I believe it was now 3 years ago, I think it was called the Tonga volcano that erupted underneath the Pacific Ocean near Polynesia, and it put enormous amounts of water vapor and sulfur dioxide into the atmosphere. But the sulfur dioxide rapidly was pulled out of the atmosphere, given that it was a ocean volcano. But that water vapor lasted about 2 years into the atmosphere, and it really warmed things up the previous 2 years. So it's something that has both short and long term impacts on climate. Okay. So, what we call, when we're looking at some of these events over time, their scientists and climatologists look at what we call the 10 indicators. We tend to focus on a warming world, right? And that is a bias, or what we call a bias of the present, because we are coming out, or have been coming out of a cooler period. in the last 6,000 years that is at least here where we live in Western Pennsylvania in North America called the Little Ice Age. But overall, we are seeing a much more rapid warming of our world than we've seen any time in roughly probably the last 150,000 years. But this also applies if you want to see a cooling world, right? It would just simply be the opposite of all of these things. So when you get a warmer atmosphere, the physics dictate that humidity goes up because a warmer atmosphere holds more moisture. A cooler atmosphere holds less. That's why the poles in the Arctic and the North Pole and the South Pole are deserts, essentially, right? So you'll see surface temperatures rising. You'll see temperatures over the oceans then rise. Sea level will rise as well. It's amazing. Every year I go down to North Carolina, I can see, once you start to hit the coastal plain outside of Raleigh, you start to run into sandy shores. Well, several million years ago, the ocean was much closer to Raleigh than it is today. Sea ice then will decrease. You see temperature over land and snow cover goes down. These last two are very important. Glaciers, snow cover, and sea ice are very sensitive to a little teeny bit of warming. They always exist on a knife's edge. So they are very susceptible, and we'll talk about this, what is called a feedback loop, right? The more snow and ice, it tends to increase a cooling trend and they expand. But if it warms and they decrease, then the land that doesn't have snow or ice on it or the ocean warms up much more rapid. So then it warms things, right? So it's pretty cut and dry. This stuff has been known in climatology for well over 100 years. Okay. All right. So let's talk about some notable past climate change. This will be very important in these next two lectures that I do on climate change in the present and the future, because one of the things we hear a lot by climate deniers or folks that try to minimize how much humans are having a outstripped impact on climate change today, they'll say, wow, there were several periods in Earth's history where it was much hotter and life did just fine. That's not true at all. In fact, there's a lot of evidence in previous extinction events that these rapid warming periods wiped out large substantial amounts of life on planet Earth. In the warmest, right, there was one about 800 million years ago, but one of the warmest that we know that we have a lot more evidence about was called the Paleocene Eocene thermal maximum. And just because that's a hard thing to say, we'll just call it the PETM. That peaked about 55 million years ago. So about 10 million years after the dinosaurs went extinct, right? And I just did a program a couple weeks ago on the evolution of birds. We believe this period when the dinosaurs went extinct into about 10 million to 50 million years after dinosaurs went extinct, that allowed birds to really take over a lot of niches and rapidly evolve into a lot of the different lineages that we see today, right? So during that time, we could have potentially seen Earth warming about 5 to 8 degrees Celsius, right? So we're talking a substantial warming within a few thousand years that also did, again, create a large number of animals and plants going extinct. We think that was due to a couple things. One, how the continent was laid out, but there was massive amounts of volcanoes that lasted. Some of these volcanoes on a continental scale were spewing carbon dioxide and methane into the atmosphere for potentially hundreds of thousands of years, right? So the warming, which lasted about 200,000 years, again, I forgot that I had that in the next one there. There's also, and we have them in our oceans today, something called methane calthrates, and they are essentially ice versions of methane deep in the ocean sediments. If it warms up enough in those oceans, that methane will massively be released into the atmosphere, very quickly warming everything. So we think it was probably a combination of these massive volcanic eruptions that lasted a long period of time, heating up coal deposits, releasing those methane calthrates into the atmosphere, and created a hothouse Earth, essentially making Antarctica and Greenland ice free, where a lot of tropical and temperate species actually thrive there, right? But since that time period, Earth has cooled, and we know that's because these Milankovitch cycles have become more regular since then. And so, for the past million years or so, the climate has switched between ice ages, right, glacial maximums, and then what we call the warmer interglacial periods, which we're in right now. We are in a interglacial period with temperatures similar to those of the past few millennia, right? And I've already mentioned why that is. However, it is clear that the orbital changes alone would not have produced these large temperature changes, either warmer or colder, and there must have been some kind of feedback effect. In these future lectures, that's what we're talking about is once Earth hits a tipping point, right? And you get rid of a lot of the ice. Earth tends to warm up. It's like a rock rolling down a hill, getting more and more momentum as it increases. It's the same thing with changes in climate, either getting warmer or getting colder. But we are definitely headed towards some of those tipping points here in the future here. If you want to see what this looks like and try to conceptualize it, this is again a similar graph that I had in my opening slide. This just shows you can see the PETM there at the top and the Eocene optimum. This is where we had a lot of tropical type plants, what is today, and we would be subtropical here in Western Pennsylvania. You would have had all sorts of crazy plants and animals we can't even imagine today. Then we'll see another cooling period where Antarctica begins to grow glaciers, and then those glaciers melt completely. And then we see roughly about 10 million years ago a really slow cooling trend. And then about 2.5 million years ago, we start to reach these rapid glacial cycles, right? And this is what's known as the Pleistocene epoch. So the Pleistocene is approximately 2.6 million years to go to 11,700 years ago, and was a period of multiple glacial and interglacial cycles. Again, we're in an interglacial cycle right now. So the most recent glacial period ended about 11,700 years ago. So where I'm sitting right now in Butler, Pennsylvania, Butler Township, I could look north from my house 12,000 years ago and see a giant glacier to the north of me. It was big enough, half a mile thick at that point, that I would be able to notice it from my house. Now, it would be pretty cold here. It would be an Arctic tundra right where I'm sitting here in my house. But that's really, when you look at the time scale of planet Earth, that's not that long ago. And so that last glacial maximum, about 20,000 years ago, you would see massive continental ice sheets covering North America and Northern Europe. And our sea levels were substantially lower, essentially because all of that water in our oceans were locked up in glaciers. So, this is where we think at least 23,000 plus years ago, humans from Asia moved into the Americas. And that's really the origin of where a lot of our Native Americans, but there was probably multiple waves over time. Here in Western Pennsylvania, closer to home, we would have been a mix of ice, right? In northern Western Pennsylvania. So parts of Butler County and Lawrence and Mercer and Erie and all those other places would have been completely under ice. But just south of it, you would have tundra, and then further south, boreal forest, like you see in northern Canada today. This gives you an example there on the left at that last maximum extent of the last glacial maximum there. The ice sheet that I would be able to see from my house was known as the Laurentide ice sheet that would have covered um, New York City and all the way huge Boston. All of these places would have been covered. All of our Great Lakes would have been under the ice. They wouldn't have existed yet. And you can see how much sea ice. So Greenland would be completely covered in a very thick glacier. There would be year-round sea ice around both Greenland and Iceland, as of course in the Arctic Ocean. And then you have the Eurasian ice sheet that would go all the way down into parts of what is today modern Europe. Great Britain would have been covered, but moving into places like France and Scandinavia would have been covered. And of course, the Alps would have had much larger ones as well. Today, you can see there on the right, this is what we see today. The Laurentide ice sheet is just a small remnant on Baffin Island, and We see Greenland still is covered in glaciers, but they are now rapidly receding. Every single year, the Arctic Ocean sea ice in summer gets thinner and retreats more and more. So we are in a very rapid and substantial warming period as we speak. I just like putting in pictures, trying to conceptualize what we would have looked like here in Western Pennsylvania. This would have been sometime in, we'll say, late spring or early fall. It's hard to say. You could see some trees that have leaves. I can't even tell if those are supposed to be conifers or not. But you could see some of the flora and fauna that would have existed. Some of these massive Pleistocene animals like mastodon and our native horses, and you see a woolly rhinoceros. And it's just interesting from the bird standpoint. What kind of birds would we have experienced here during this time? I tend to think again, it would be very similar in a lot of ways what you would find up in the high Arctic today near northern portions of Hudson Bay and up into the Arctic Circle. So it's interesting to contemplate how different things would have been. Okay. We do know in that time, in the last 2.6 million years, that there have been at least 17 cycles of glaciers advancing and then retreating in these interglacial periods. And we know for a fact that these Milankovitch cycles, but also not too far behind, the CO2 levels in the atmosphere and then feedback loops are what made these glacial periods as well as the interglacial periods work. And you'll see a graph here too. When CO2 levels at the height of the ice age and in that maximum, CO2 levels were down below 180 parts per million. So Earth wasn't able to hold as much heat because of these Milankovitch cycles. And then the feedback loops with greater glaciers just cooled things even more, right? Glacial periods lasted substantially longer than the interglacial periods. And the last glacial period that we experienced began about 100,000 years ago and lasted roughly until about 25 to 20,000 years ago. So once we hit that, we start to have very rapid warming in the beginning of our current interglacial period. But after a few years, right, we see a very rapid return to glacial conditions. And this is called the Younger Dryas. So Dryas is based on a type of flower that you find in Arctic conditions. And it was an abrupt cooling event that interrupted a warming trend and occurred roughly about 2,900, or excuse me, 12,900 years ago to about 11,700 years ago. It had major impacts on human populations on planet Earth. So I could do a whole program just on the impacts the Younger Dryas had on humans who were hunter gatherers across planet Earth at that time. We think that event as well is probably what sparked the early farming revolution in the Fertile Crescent Levant as a result of this, right? So the period is characterized by return to near glacial conditions in the northern hemisphere. And what we think caused it, believe it or not, was the massive amount of fresh water that broke through the St. Lawrence River into the Atlantic Ocean, and it stopped almost completely what we call today the Gulf Stream. Completely stopped it, and so that heat transfer ended, and it was like a return to glaciers. There's a goofy movie called, I think it's called A Day After Tomorrow, where it focuses on climate change. It's a Hollywood movie, and the Gulf Stream shuts down, and it's the end of the world. And again, that's not science. That's just Hollywood, but it's based on something similar to that. So just to not beat a dead horse, but just to reiterate here, right? During the most recent glacial maximum, about 20,000 years ago, global temperatures were likely about 5 degrees Celsius or 10 degrees Fahrenheit colder than they are today. And remember, this is averaged across planet Earth. This isn't just here in Western PA. We think it could have been as much as 15 degrees Fahrenheit or about 8 degrees Celsius colder than it is today, right? Some areas experienced even more extreme drops. Others, right, were some ways comparable to what they are today. So it wasn't evenly distributed around the planet. And this is important when we talk about the medieval warm period here. Just briefly, we're going to come up to it in the Little Ice Age, because just then, as now, it wasn't you didn't have an ice age with woolly mammoths and glaciers on the equator, right? The tropics were still very warm. There were still rainforests in certain locations, but it was much smaller. So the tropics were still very, very warm, but substantially drier than they are today. So again, all of these things, orbit, CO2 concentrations, feedback loops, and ocean currents were the main drivers then as in now. The big culprit in these changes, and it's a response to how warm or cold our atmosphere gets, is carbon dioxide. We have very, very strong records now. Believe it or not, I should have updated this because we now know we have, I think they just did an ice core sample from Antarctica that goes back 1.2 million years ago. So inside those little air bubbles trapped in the ice, they can actually measure what the atmospheric carbon dioxide was. And you see, again, we always say correlation is not causation. We say that in science. But look at the two graphs connected there. Temperature on the bottom correlates very strongly with the amount of carbon dioxide in the atmosphere. Again, this is not 30 years ago they just discovered this. This has been known for well over 100 years that the amount of carbon dioxide you find in the atmosphere is not the only, but it is a major driver of Earth's temperatures and climate over a period of time, right? So you see very, very strong correlation between the two. Okay. And so, how do we know these things, right? I mean, people often say, "Well, yeah, the woolly mammoths and the hunter gatherers in the ice age didn't have thermometers. So how do we know these different things? How could you say it was 10 degrees Fahrenheit or 5 degrees Celsius colder than it is today, right?" Yes, right. We know that before about 150 years ago, all of these temperatures are estimates or reconstruction based on what we call proxy data. But that does not mean we cannot create a very accurate temperature reconstruction. In fact, every year new science comes out that shows that we can actually really, really get down, sometimes within decades, of what the temperatures were. So it's really fascinating field that a lot of people are making major advances in. So we can look at things like ice cores and really strongly determine what the temperature was based on the gases in the ice, but also how the ice either grows or doesn't grow. It produces like tree-like rings in there annually. Ancient pollen shows us what plants live by, and they're very, very tied to the temperature. And then what's called isotopic ratios. So we can look at things like seashells that were around and deposited in sediment and really get a fine tune of what some of these temperatures were because that's how they're produced in certain temperatures as well. So it's become very, very accurate in recent years. And I've already mentioned, it's certainly true that Earth has experienced some extremes in the past that were either much warmer or much colder, right? But these main factors that cause those past warm and cold periods, the ebb and flow of climate changes, are very well understood. So you hear a lot of times, oh, there's so much uncertainty. How can we predict the future? That's not true. In fact, the certainty there is very, very strong. And every year we're filling in the gaps and we're showing the picture that we believed is actually, in some ways, much, much more accurate than we originally thought. So we do know and we can make very strong predictions about the future based on this. Okay. Moving quickly here, because I want to get into the medieval warm period and little ice age, the Holocene climactic optimum. This is another one that I hear all the time when I teach or I talk about, climate change. So this is a fancy, the Holocene means the more recent era. There was a period, people say 6,000 years ago, it was much warmer than it is today. So therefore, the conclusion they come up with, humans are not causing climate change today, right? Well, there's a couple faulty parts to that reasoning. One, this Holocene climate optimum probably seems more localized, where we can actually get better ideas of what this proxy data is. But it was concentrated essentially in the northern hemisphere in the summer, where we are today, right? Parts of the northern hemisphere, North America, and Eurasia. Um, but the average global temperatures at that time we found, very strongly did not exceed those of recent decades by much. And actually, the newest evidence is they haven't at all. It was still actually cooler than it is globally today, right? And once again, same things that we know, right? Orbital variations, um, but vegetation and sea ice changes, all those feedback loops caused that about 6,000 years ago. And it didn't last very long either. Okay. All right. So I've really gone through very rapidly. If 45 minutes plus is rapid for you all, hopefully you're still with me here. We're going to start getting into a little bit closer to the present and understand some of this more recent climate change, right? So we talked about the after the Younger Dryas, the Holocene climate optimum. Generally speaking, the peak was about 6,000 years ago. Okay. The recent Holocene, which we're going to focus on here, is the last few thousand years. So we're going to say roughly 2,000 years, what we call so CE, after the Common Era, which used to be called AD, right? You will see regional warm periods that have names like the Roman warm period because the records that we have were based on Roman written records of that time. We can also contrast that there are some surviving records in China at that time. But my family, that was Slavic people, become the Poles or the Scandinavians, the Germans, they weren't writing any of this stuff down. So we don't know enough across planet Earth because not everybody was writing about this stuff, right? Same thing in the medieval warm period. It's because it's very Eurocentric because that's who, at least early on in these early researchers, studied the people in Europe that were writing about this. Then we're going to talk about the poorly named Little Ice Age. A period known as Little Ice Age occurred from roughly, again, this is controversial, 1300 CE to about 1850, give or take 50 years CE. And it was a minor cooling period in the northern hemisphere. This was not a planet-wide event like Younger Dryas or, the PETM. This was a more regional thing, and to call them the medieval warm period, we have found very, very strongly that it really was focused in a few places, and other period parts of the earth at the same time were much colder than they were afterwards. So you got to keep in mind a lot of this stuff is really focused on Europe or where Europeans were. Okay. Let's start with the medieval warm period. This is some of the climate research with history that I've done a lot because there's a lot of really interesting things that how human societies in Europe reacted to this, right? So this, what we call the medieval warm period or the medieval climate optimum or the medieval climate anomaly, however you want to describe it, was a time of, generally speaking, and I can't stress that enough because there were still cold periods in this period as well, right? In the North Atlantic region, that if you measured it over from about 950 CE to about 1250 CE, generally speaking, averaged out, it was much warmer than the previous, say, 900 years, excuse me, and then definitely much warmer than what would happen from about 1300 CE to about 1850. Okay. Climate proxy records show peak warmth occurred at different times at different regions, especially in Europe. But this is where you see Europe's mass populations really start to rise between this time period. And especially from about 1100 to 1200 and 1250, this is where the mass cathedrals, these things, these in France and parts of Germany, are building these massive cathedrals because they have enough food, the population is very high, they're having regular, bountiful harvests. At least in Europe, it's creating a large surplus of foods. They're increasing their locations in some marginal areas that now they couldn't farm before, but it's warm enough they could farm. Even England at this time, they haven't had viticulture or grape and wine production going since the Roman era, but it's warmed up enough that now some folks in England are starting to try to replicate wine growing like France, right? So it was a very, very optimal time that we see Europe's population greatly swell. If you look across planet Earth, right, Parts of Eastern, at least North America, and parts of the Midwest also experienced this same warmth, but other areas did not. So Antarctica did not, parts of Alaska did not. The Southwest experienced severe droughts. In parts of Mexico and Central America, they actually cooled slightly. So this is a really regionalized type of warmth here, right? Um, it's really interesting. So here, closer to home in Western Pennsylvania, this is where you see around this time, about 900 CE, maybe a little bit before, maize, or we call corn, and beans, and some squashes begin to spread north from Central America, and finally, with this warmer temperature, these maize plants or corn begin to be acclimated to and can be grown here in Western Pennsylvania. And what this does in this time period, roughly about, say, 400 to 200 years before Columbus's voyage, is we see mass population increases here in Eastern North America by Native Americans. Further to our west, a place called Cahokia, which is near St. Louis today, they had a city that had roughly about 40,000 people, 40,000 Native Americans living at this time. So it was beneficial to some populations where this warmth occurred. However, right? Oh, and one last thing I do want to mention, this is also, since I just got back from Newfoundland and was there last year, this is when the Norse or the Vikings start settling places like Iceland and Greenland and come to northern Newfoundland because for the first time in centuries, there's not a lot of sea ice during the summer, so they could actually sail. However, this rapidly changes by about 1300. And it's very controversial when it actually began, right? And again, it began in the North Atlantic region. Not all of planet Earth cooled at this time. Some places got warmer, but this little ice age is focused really on this North Atlantic region, which we're going to talk about here. And again, it was not a true ice age, number one, and it certainly was not of global extent. So it was nothing like what we experienced in the Pleistocene. Um, Both historians and scientists really want to change the name of this because, again, ice age is not a good description. It is really broken down into three distinct cold periods. So the 1458 to 1552, we see, at least in Europe, becomes much, much colder than it was in the medieval warm period. And there are a ton of famines. The Black Death rages across Europe, reducing Europe's population by about a third. I mean, substantial loss of life. But this colder, wetter environment also plays a part in that. Then we see the coldest period by far is 1600 to 1720. This is really important because this is also when these European countries like France and Britain and Spain are settling, or at least attempting to settle North America. And a lot of them fail because the little ice age has such an important impact that it basically causes a lot of these early settlements to fail. So one of the things I think is that had they failed en masse, like they did for the Spanish, because the Spanish actually were settling in places like South Carolina and Georgia in trying to take over the rest of North America. If it wasn't so cold and dry at this time, they may have succeeded. And I may be speaking Espanol to you right now rather than English, right? And then lastly, we see the 1840 to roughly 1880. It depends. This is more regional than the other ones. But that was sort of the last hurrah of what we call the Little Ice Age. Several causes have been proposed, including cyclical lows in solar radiation, once again, well known. But we see, unlike the medieval warm period, heightened volcanic activity. And we could see this in the ice cores from Greenland and Antarctica. And we see them very strongly corresponding with the cool downs afterwards. And there was a lot of volcanoes at this time. Also decreases in human population, right? So if you know anything about Genghis Khan, he wiped out millions of people across Asia and Europe. The Black Death certainly had a huge impact as well. So that changed a lot of land use. And we believe, and this is, again, still circumstantial, but the diseases that Native Americans sort of experience through contact with Europeans or other Native Americans wiped out millions of Native Americans before they ever saw a European. So all this would have caused humans to stop, farming and doing things that release CO2 and methane in the atmosphere, reforesting vast amounts of areas and sucking more carbon dioxide out of the atmosphere, right? Just to give you a time frame going back to the 2000 years, right? You can see, and this is global, right? Believe it or not, even in what we call the medieval warm period, there was still a slight dip in periods of time there, right? And when we call that, it was still cooler than what it is today across planet Earth. You then see once again, and that's why we have regional on there. The Little Ice Age, again, also regional. You see some modest dips in temperature and focused on those time periods that I mentioned. But you notice after about 1850, and this is what's known, maybe you've heard before, as the hockey stick, you see a very massive upward amount of our global temperature. And that is due to humans burning fossil fuels and other land use changes, okay, adding CO2 and methane into the atmosphere. One of the cool things that I've done, and I didn't invent this. There are historians, environmental historians, that research a lot of the paintings from the Little Ice Age. That kind of gives them an idea about how different the climate was in their winters compared to what they are today. In fact, their summers in Europe and North America probably weren't too much different than they are today, but it was the winters that are substantially colder. What you see here, this is 1608 on the Thames River in London. Was an ice fair. So it got so cold in these winters in the quote Little Ice Age that the Thames in London would freeze, and same thing in continental Europe, and they would have ice fairs. So they would have these different booths of foods and games, and they would have all sorts of fun in the middle of winter on the frozen Thames, right? And you would have boats that would be on like little skis that people would pull, and they would, sail on there. So it's really cool to kind of get an idea of what the climate was like during the Little Ice Age based on some of these paintings, right? In Europe, in the Alps, a lot of these glaciers that were receding during the medieval warm period rapidly start to advance in the Alps, particularly in France and Switzerland and Italy, that they start swallowing villages that had moved up the Alps in the previous couple hundred years during that medieval warm period. They would often bring out Catholic priests, and they would do sort of I guess, prayers in the local chapel to try to reverse the ice. Most of the time that didn't work, but it's interesting to see through the art of how foreboding a lot of times the ice starts coming down out of the mountains on annual basis. It's really, really interesting to see how this played out. My mom has this painting in my parents' house. So this is a famous painting. I think his name is Robert Walker. He was a parson or pastor in England. And today, this part of England doesn't get cold enough to get these lakes to freeze over. But at this time, he's ice skating in the middle of winter. So this is a relatively, I don't know, I've seen it in a number of other different places. One thing to think about is in closer to home in American history, right? During the Revolution, you may have learned or studied about how Valley Forge was a really trying time for the Continental soldiers of Washington's men overwintering at Valley Forge. And that winter that they were there, 1777, 78, was one of the coldest winters in probably a couple hundred years. And that was, again, part of the Little Ice Age that made our winters substantially colder and longer, really, than they are today. So when you look at the art, even events like the American Revolution were impacted by this Little Ice Age. Okay. So here, closer to home, Western PA, this cooling really begins much later, roughly about the latter part of the 1500s CE. We see much cooler or sometimes much colder winters and springs, right? You could have frost at this time period all the way into early June. Our summers would have been similar, maybe not as warm as they are right now in July and parts of August, but pretty comparable, right? But you would also have more droughts than we had today. And we could see that in the record. simply because a cooler atmosphere, even though it's summer and it's still warm, has less moisture in it. Evidence from tree rings and early historical records show that colonial regions experienced severe, persistent droughts at various times in the early 1600s, um, definitely impacting settlements in New England, the Carolinas, and southeastern U.S. In fact, we know if you've ever heard of the Lost Colony in Roanoke in the Outer Banks of North Carolina, where they carved Croatan on the tree, we're almost certain that that was a failure due to a massive drought in that part of area of North Carolina in the southeast. It was probably the worst drought when we look at tree rings and some other proxy records that that area has experienced in maybe 2,000 years. And interestingly enough, so prior to what we call the French Indian War period, right, those Native Americans that lived here when George Washington was coming at Fort Necessity and Fort Duquesne and Fort Pitt and all that fun stuff, none of those Native Americans were native to this area. Those were all refugees from somewhere else. The original Native Americans, who we don't know what they called themselves, we have generically called the Monongahela people. And there is very strong evidence that at least one of the factors, including warfare by the Senecas, but drought was a major factor in destroying these Native American communities and wiping them out prior to Europeans coming here to what is now Western PA. This is a representation, believe it or not, along the Yakagani of what one of these original Monongahela villages would have looked like. But once the five great nations, the Haudenosaunee, interacted with the Dutch and then some of the English in New England, they got firearms where these people didn't. We know that they raided them, but it seems their populations decreased also very strongly due to the drought that hit Western PA in this time period, right? But this is very important to understand. Okay, just because it was the little ice age, and over time our winters were generally speaking very cold, right? We still had periods of very unusually warm winters. 3 years in a row in the 1790s. We had some in the early 1800s, the 1830s, even in the 1880s, right? I've done a lot of research on this, and there's all sorts of newspaper reports and journals talk about how warm it was around Christmas and all this other stuff. That again is weather, not climate. That was due to things like a very powerful El Nino, which warms up the atmosphere because it brings in a lot more heat in the Pacific. So that just because again there was warmer winters then does not mean that the climate overall in this area had cooled pretty substantially, right? We're going to talk about this year without summer, 1816, and that was due to a volcano that erupted in Indonesia back in 1815. But it's interesting that year. There was frost in every month of the year in Western PA except July. We had snow here in Pennsylvania in June. New England had snow in June as well. They had a foot in some of the higher elevations, and they had frost every single month that year. So it was a major climate event but it often gets exaggerated as these things do. The last time that we're able to here in Western PA see frosts that and freezes that occur in June. Do you remember the last time that happened? Neither do I, because it hasn't happened in our lifetime. The last time was really in June of the 1850s. It froze several times in early June, and it really hurt crops, right? It shortened the growing season. So frost returned in early September in some of these years, right? So it was a major problem. But by the end of the 18th century, we start to see, or excuse me, 1800s, 19th century, we start to see the climate begins a warming phase, and it has been accelerating mostly due to humans, right? We're going to finish up, and I'll open any questions. I just have a couple more slides here. What is called the year without summer began the year before, July 1815. So Mount Tambora, which is a volcano on the island in what is now Indonesia, right? The Dutch East Indies, the Dutch controlled it, erupted and is considered one of the most powerful volcanic eruptions in recorded human history. So think about this. It ejected almost potentially 11 cubic miles of rock pulverize that material and put it into the atmosphere. The amount of ash and sulfur compounds was as much as 6 times that any volcano has put into the atmosphere in probably the last 45,000 years. So it was a huge amount of material that reflected sunlight and dispersed and substantially lowered global temperatures for a single year. And it's known as the year without summer. Okay. We do know for a fact that the northern hemisphere that year in 1816, right, cooled much more than almost a degree Fahrenheit, but that was the global one. We think anywhere between 2 to 4 degrees Fahrenheit. And this cooling led to some of the last big food famines in Europe and directly or indirectly caused roughly about 90,000 deaths across planet Earth. So it was the second coldest year in the northern hemisphere since around 1400. In the 18, and I think the coldest was 1608, and the 1810s are one of the coldest decades on record, right? So it created things, this climate anomaly created things like typhus epidemics in Southeast Europe and the Eastern Mediterranean. Closer to home in New England, lots and lots of livestock died because there wasn't enough hay. And they repeated failed corn harvest. A lot of New Englanders moved to Ohio and other places further west, so it really accelerated pioneers and colonization of Native American lands to our west. Food prices rose sharply in US and Europe, and there was lots of food riots and arson and looting, right? So it was the worst famine really in the 19th century. This was also the year that the woman who wrote Frankenstein, so she was up in a castle and all that gloominess that inspired her to write the book Frankenstein, right? So this is Mount Tambora today. If you see, it's still recovering from that massive eruption that used to be substantially larger. And you could see this is looking where the biggest impacts were across planet Earth. You could see just north to us, right? It got substantially cold. We had frost in Western PA into June, right? It got very, very cold that year. But the year without summer, that is a exaggeration because even that summer, there were times where it got very warm, right? But overall was much, much cooler than we normally get on average today. This is an artist, a more modern representation of what it would have been like that year. And you imagine if you're a subsistence farmer, like most farmers were at this time, if you lose your corn crop 3 times to frost or freezes, you're going to be in some serious trouble for not just your livestock, but some of the food that you depend on as well. So that short-term climate change, or excuse me, that short-term anomaly, because it's not real climate since it lasted a year, but it had a major impact, right? My last slide here is, and this is leading up to our next presentation on climate change in the present. You could see then as we get into the 20th century, glaciers that had really advanced during the Little Ice Age in the North Atlantic and parts of the northern hemisphere start to rapidly recede in the 20th century to some points. And now this thing is dated by 10 years. A lot of those glaciers are completely gone at this point, right? And you can see this one. This is the Muir Glacier in Alaska. Looking back to the 1920s, essentially, you could see that entire glacier filling the valley. By the 70s, it had receded pretty substantially. And then today below, that glacier has moved up several miles in this valley. This from the same spot, you can now see green vegetation growing. So we have moved it into an era of very, very rapid climate change due to humans, and humans being the primary driver of climate change through our burning of fossil fuels and emitting large amounts of CO2 into the atmosphere. It's my last one, I promise. This is Glacier National Park. A lot of those glaciers are now completely gone. And they are saying if things continue as they are, most of those glaciers at Glacier National Park in Montana will be gone by 2040. So if you've never visited, 15 years may seem like a long time, but that's definitely not a long time there.